During last lecture, we started with this strength failure theories. So as far as concerned with this composite material, we already know that composite is not specific of one kind. Whatever our assumptions in solid mechanics, in analysis of mechanical element, in strength of material, that material is isotropic. But that is not true in case of composite material. Material may be isotropic, maybe material transversely isotropic, maybe it is monoclinic, maybe it is orthotropic, maybe it is anisotropic, anything. So anything can be possible in case of composite material, and that's why analysis of composite material is very, very crucial, difficult, and what we can say as the task where there are many challenges. Is it okay? So there is large scope in this field, in research also, as well as in profession also, because many softwares presently also not have the facility to make analysis of the composite materials which have properties beyond orthotropic, anisotropic, or any such a kind of problem if it exists, then how such can be analyzed. So that is one of the challenge in many softwares presently also, because the kind of theories that are used for the analysis of such a composite material, that is still not known. Presently, a number of softwares are used higher order shear deformation theory, and that particular theory was developed by Tarun Kant or Jane Reddy. So such a scientists are there those have developed this kind of theory, and first order shear deformation theory, higher order shear deformation theory, classical plate theories that are used in case of composite material. However, we should go step by step for these such a kind of theories. Besides this, first of all, we should start with the isotropic material and whatever the fundamental things which we have studied up till now. During last lecture, we have seen this particular example. In that example, the cross-sectional area of the rod is provided, ultimate tensile strength is provided, ultimate compressive strength is provided, and ultimate shear strength is provided. And it is asked that what is the maximum load that can be applied using maximum stress failure theory. So maximum stress failure theory, how this theory is used. That problem, if we try to solve here, if we take the reference of Morse circle analysis, then maximum principal normal stress theory, with the help of this, we can say that the normal stress is half of that, whatever the maximum load P is applied here. So based on that, on first step or on first way of analysis of this theory, we are considering that it is sigma is equal to P by 2. Is it okay? So when we consider this P by 2, then again question comes that which P should we refer, because here we are using the different strengths, and while using the different strengths, we have come to know that ultimate tensile strength, ultimate compressive strength, ultimate shear strength, all strengths are different. If we refer the ultimate tensile strength, then that is 25. If we refer the ultimate compressive strength, then that is 95. And if we use ultimate shear strength, then that is 35. So if we use the ultimate tensile strength, then it is 25, which is lesser than ultimate compressive strength. So besides 95, we are giving the preference to this ultimate tensile strength 25. And that's why here we are taking for the reference that P by 2 is equal to 25 into 10 raised to 3. So this is the sigma. Is it okay? So this is the stress. So stress into 2, here we are getting the P should be less than 50,000. If we take the compressive strength into the calculation, then it will become 95. Then 95 into 2, it will become 190. And as compared to 190, 50 is very small. So this 50,000 is preferred in this first criteria when we are considering a regular kind of stresses. But if we consider the shear stress, then maximum shear stress is P by 4 and acts at cross section is at 45 degree to the plane of maximum stress. Already in analysis of mechanical element, you have studied the principal stresses and strains. And while studying that principal stresses and strains, we know that maximum shear stress is P by 4 and it acts as a at a cross section 45 degree. So that reference is also taken because the ultimate shear strength is given as 35. So here if we take P by 4 is equal to 35 into 10 raised to 3, then P we are getting as 140,000 pound. Here it is 50,000 point. So with first criteria and with this second criteria, it is found that the failure will happen in case of tensile and the maximum load that will bear it is 50,000 only. So that 50,000 load should not be crossed. Beyond this particular value of 50,000, then it will indicate that this material gets fail if we cross this particular limit. And that's why the maximum load is 50,000 pound. Is it okay? So this is the way through which we have analyzed this maximum, this particular problem by maximum stress theory. Is it okay? The notations which usually used in case of this failure theories, instead that this sigma refers to the stress, then this 1 refers to the direction 1. Is it okay? Because reference direction is considered 1. And here T represents as a transverse. Is it okay? So here tensile. So sigma 1T that represents the stress in direction 1 and which is tensile in nature. Is it okay? ULT, that is the ultimate. Is it okay? Because yield and ultimate, both kind of stresses are there. So this particular notation, when it is used, sigma 1 raised to T base to the base ULT, that indicates that stress acting in direction 1 which is tensile in nature and it is ultimate tensile strength. Is it okay? Similarly, if T is replaced by C, that indicates that this is the compressive stress. Is it okay? So tensile and compressive, that we can understand with this notation 1 and notation 2. Notation 3 indicates base sigma T raised to T to the base 2. Now 2 represents that this is the direction 2. Is it okay? In second direction, the ultimate tensile strength is this particular notation. And if here C is used, then on second direction, what is the compressive strength? That is the notation used here. And when tau, this particular notation is used, then in the direction 1 to 2, in plane 1 to 2, ultimate in plane shear strength, that is given as tau 1 2. Is it okay? So unlike this stiffness parameter, these are the strength parameters, and these are defined in case of lamina like this. Is it okay? So maximum stress failure theory, as far as concerned with this maximum stress theory, the stresses or strains in the global axis of lamina, one can find the stresses in the material axis by giving the equation like this. Is it okay? So here, if we use this particular formula, the lamina considered is a failed if minus sigma 1c is less than sigma 1 is less than sigma 1t, or see here, minus represents compressive, plus represents tensile. Similarly, in direction 1 and direction 2, same thing is there. So for second direction also, whenever it is negative direction, negative sign indicates it is compressive, positive sign indicates it is tensile in nature. Same thing is possible with the help of shear stress also. Is it okay? Minus indicates compressive and this is the tensile. Is it okay? Both are, maybe it is compressive, tensile, both are in ultimate values. Is it okay? So minus sigma 1 compressive stress in direction 1 and in direction 1 tensile stress. Is it okay? So this particular sigma 1, now only we have solved this example, so you know better that how this sigma 1 is defined. And negative and positive, that indicates that this negative is shown here, positive is shown here. It indicates that if tensile and negative, it is compression in nature. Is it okay? Like this. So let us take one more example to understand this particular concept more properly by maximum stress failure theory. Is it okay? So find the maximum value of S is greater than 0 if stress sigma x is equal to 2S, sigma y is equal to minus 3S, and sigma tau xy is equal to 4S. Is it okay? So sigma x is the stress acting in x direction, sigma y is the stress acting in y direction, and tau xy is the shear stress. The values are given in terms of S notation. Is it okay? So sigma x is given as 2S, sigma y is given as minus 3S, and shear stress tau xy is given as 4S. Is it okay? It's particularly applied for 60-degree lamina of graphite epoxy, and then by using maximum stress failure theory and the properties of unidirectional graphite epoxy lamina, we have to solve this example and we have to identify the value of sigma 1, sigma 2 and tau 1, 2. Is it okay? So whenever we are solving this example, first of all, whatever the matrix we were used or what matrix we have referred in the macro mechanical analysis, same thing now we are going to refer here also. Is it okay? We know how this macro mechanical analysis was carried, and in that how the relationship between stress and strain has been established. Is it okay? So this is particular stress, this particular rho is the stress. Similarly, now in this case, if we consider this as sigma, this is also stress sigma x, sigma y, and tau xy. You may consider the principal values of the stress because these particular values are for 60-degree lamina. Is it okay? So principal stress and principal strain, that concept once again we have to study, we have to carry here. Sigma 1, sigma 2 and tau 1, 2 are the principal stresses, and these values of sigma x, sigma y and tau xy are the stresses in the direction of x, y and shear stresses. Is it okay? So that along with their signs that are used here, and these values of the matrix which are shown here. So in computer graphics we have studied the rotational matrix, transverse matrix, rotational matrix, that we have already studied. Is it okay? So when we go for this table 2.1 here, we get the values of this glass epoxy, boron epoxy, etc. And as far as concerned with this equation 2.94, is it okay? Here this equation 2.94 is used. In that equation, already in macro mechanical analysis, what things we have carried, that is given here. How we have calculated the value of S11, how we have calculated the value of S12, how the value of S13, S22, S66, that was carried, that we know. And how this matrix in the form of these stresses has been expressed, that also we know. Is it okay? We have expressed earlier this matrix. See here. But this is the relation between stress and strain. We are not interested in the relation of stress strain. Now we are interested in the relation of principal stresses and stresses in the direction of x. Is it okay? And that's why this matrix in terms of this that we are going to use, and that we will refer here. Is it okay? So here, as far as concerned with this particular 60-degree angle lamina, because in this example it is mentioned that this is 60-degree angle lamina. So sigma 1, sigma 2 and tau 1, 2, that values are provided here. Sigma 1 is 2, sigma 2 is minus 3, and here tau 1 is 4. Is it okay? So that values are referred here, and based on that the values of Q are identified. Q is considered to be the inverse matrix of this S, because these values we will get based on the translation and rotational factors. Is it okay? Because in computer graphics we already known that if this X, suppose here this particular example you can analyze with the help of this local and global axis, because one axis we are in this angle lamina, if reinforcement is present in this direction theta, which is shown here. Is it okay? So theta is the angle. So here you can see this angle, particular angle with this X. This is the value where this theta is present. So the theta represents the angle of this reinforcement with reference to x-axis. If this is exactly equal to x-axis, then sigma 1 will be equal to sigma x, and sigma 2 is equal to sigma y. But this is not happening. These reinforcements are having certain angle, and that angle is angle theta. Is it okay? Which is shown here. And that's why the concept of sigma 1, sigma 2 come into existence. Otherwise, sigma x and sigma y, that is sufficient. If reinforcements are in the direction of x or in the direction of y, then there is no problem. But if that is not in the direction, in that way, then we will come to know, we will have to take the reference that this x with reference to 1 and y with reference to 2 we will have to, because this line 1 to line 2 both will be perpendicular to each other, and this line x to y that are perpendicular to each other with usual notations. Is it okay? Whatever the notations usually we are using, with that usual notations, this x is perpendicular to y and 1 is perpendicular to 2. Is it okay? 1 is at an angle theta to this x, and in present example that angle theta is given as 60 degree here. Is it okay? So here we can consider sigma x, sigma y and tau xy, and relationship between sigma 1, sigma 2, tau 1, 2. Is it okay? Here we can clear cut understand for this sigma x, sigma y, sigma 1, sigma 2, both are different, sigma tau xy and sigma 1, 2, that we can refer here. So with this particular value of sigma x, sigma y and tau xy, or sigma 1, sigma 2 and tau 1, 2, here we can analyze that difference. Is it okay? So stress in direction x, y and shear stress, here this translation matrix is used. Is it okay? So this transformation matrix or T matrix, inverse of that is carried, and with that matrix if it is multiplied for sigma 1, sigma 2 and tau 1, 2, then we will get this sigma x, sigma y and tau xy. Is it okay? For that purpose here you may use this particular translation matrix. Is it okay? So this Q and S, with the help of this matrix is generated here, and likewise here also we are using this transformation matrix. Is it okay? So this transformation matrix, which is with the base of computer graphics, and it is given as C square S square minus 2SC. This particular matrix you have used in computer graphics, where this C represents cos theta and S represents sin theta. Is it okay? In present example, that theta is 60 degree, and that's why C, which is cos theta, and S, which is sin theta, with the help of this transformational transformation matrix, the values we should put here, and after putting that values, we will get the value of sigma x, sigma y and tau xy. Is it okay? So this particular equation sigma y, sigma x, sigma y, tau xy, which is again represented in terms of strength, and before using this equation there was sigma 1, sigma 2 and tau 1, 2. Is it okay? But here what is happening? Here one Q has been added here, and this Q represents here that this is the matrix, which is earlier in macromechanical analysis we have seen the relation between stress and strain. When we represent the stress and strain, we know the stress upon strain is equal to Young's modulus, and that's why stress is equal to Young's modulus into strain, and that's why this is the stiffness matrix. Is it okay? Because elastic stiffness we call E as a, and this is the representative of E. That's why this is stiffness matrix. Q is representing the stiffness matrix. Is it okay? So based on that, this strength epsilon 1, epsilon 2, and this can be calculated here. We can understand this how the relationship between strengths, principal strengths and strain in the direction of x, y, z is also given here. Is it okay? So we will not go much in details of that, because if anybody wants to take this problem as a problem of analysis for their MTech thesis, then you can take the references here. If anybody is working in the composite material, and if anybody wants to go for analysis of the composite material, then this is the fundamental for that. Based on these fundamentals, one can go for the analysis based on this angle lamina. Is it okay? Whatever may be the angle lamina, with reference to that, this example can be solved here. Is it okay? So this much about this case, how this theory is working, and how this transformation matrix and the relationship between principal stresses and the sigma x, sigma y has been carried out. So now whatever the example we are observing now, in this present example, we have to use the maximum stress theory in order to identify the safe limit of the stress, and based on that safe limit of stress we can go for analysis of the maximum load what can be applied, and based on that applied load we are going to identify the maximum value of load that can be given here. Is it okay? So let us come to our example. In this example we were studying, we were using this equation for the references, and here we have used this particular maximum stress theory here. So sigma 1 is given as this point. So this particular matrix you can understand now. This transformation matrix sigma 1, and this is sigma x, sigma y, and tau xy. Is it okay? So with this multiplication we will get sigma 1, sigma 2, and tau 1, 2. Is it okay? So ultimate strengths of unidirectional graphite or epoxy lamina. So that is here stress, one stress, the tensile stress, compressive stress, that we can see here, tensile and compressive stress here, shear stress also that is shown here. Then using the inequalities of the maximum stress failure theory, here you can use that by solving this equation we have got this principal stress, principal tensile stress in direction 1, principal compressive stress in direction 1, principal tensile stress in direction 2, principal compressive stress in direction 2. This is shear stress 1, 2. So how these equations that are put here, that we can see with that particular values here, equations are put by using the maximum stress failure theory, and here we get that all the inequality conditions, and s is equal to, so for this 0 is less than s or 16.3, because these particular values if we try to identify, we will come to know that the value of s in this minus 875.1 to 875.1, minus 14.73, minus 16.33, 16.33. So if s is in between 0 is less than, s is less than 16.33, based on these three assumptions, we are getting that the maximum value of s that should be in that range only. So that's why the maximum stress in the x direction, maximum stress in the y direction, and maximum shear stress, that values that are identified by putting s is equal to this 16.33 in above equation. Is it okay? So based on that, the values of sigma x, sigma y, and sigma Z are identified because we are considering sigma x is equal to 2 times of this S. So S value with this analysis we have got as equal to 16.33. So 16.33 into 2. So that is approximately 32.66. So that is the sigma x. Then here in this example, this sigma y was given as minus 3s. And if we use this minus 3s here, then 16 into 3, 48, and 33 into 3, 99. So minus 48.99, that is the sigma y. And for that tau xy, what is the case that it is given as equal to 4s. Is it okay? So 4 into this 16.33. So 64 and this into 4. So this is 65.32. That is the answer we are getting with the help of this analysis of this S value. And this S is identified with reference to this principal stress and the sigma x relationship. With this we got S. Then we identified these principal stresses in tensile and compressive directions, shear directions. Then substituting that values here, inequalities, maximum stress failure theories, and then identifying the value of S, which we got sigma x, sigma y, and tau xy in this way. Is it okay? So this about the maximum stress failure theory. Similar examples are there for maximum shear stress stress theory also. That you may refer. A book is available with you. That is already present on this Moodle server. You can anyway any time you can download it and you can use for this examples. Is it okay? So remaining examples of this maximum stress theory that I will not go, but before that we will go for the next concept of the failure envelopes. Is it okay? That we should know, because failure envelope is nothing but the region in which region this particular material or this particular component is safe. Is it okay? So failure envelope is nothing but the three-dimensional plot, and where the combination of normal and shear stresses that can be applied to an angle lamina just before failure. Is it okay? Because drawing three-dimensional graphs can be time consuming. One may develop failure envelope for constant shear stresses and then use two normal stresses, sigma x, sigma y. Together we can identify value of maximum stress in x direction, in y direction, in shear direction. And then at the same time we may identify the values of sigma 1, sigma 2, sigma 3 like this. Is it okay? So here we can have this flexibility with the help of this failure envelopes. Is it okay? So this sigma 1, sigma 2, tau 1, 2, using this proceeding inequalities, this can be identified here. Is it okay? So in different type of failure envelopes we can see these are available. Is it okay? Then let us come to the next concept, that is the maximum strain failure theory. So initially we were studying the maximum failure stress theory, but now here it is maximum strain theory. So as far as concerned with this maximum strain failure theory, it has been observed that the same kind of equation of set which was used for the maximum stress theory is once again used for this maximum strain failure theory. However, the lower limit and upper limit, that things which are shown or which can be used here, for that purpose once again we are taking same set of equation, but rather than using stress as a criteria, we are using the strain as a criteria here. Is it okay? So maybe compressive or maybe tensile. The nature may be tensile or compressive, but the set of equations are same. Minus epsilon 1 C is less than epsilon 1 is less than epsilon 1 T. Is it okay? So compressive in nature, tensile in nature. So for compressive in nature we are using negative sign. For tensile in nature we are using positive sign. This strength epsilon 1 is strain epsilon 2 and strain epsilon tau gamma 1 2. Is it okay? Here we are using the notation gamma 1 2. With usual notations, we should understand this direction 1 2. So if this is the particular direction which we are interested, this particular direction, if this direction we are taking into reference, is it okay? As far as concerned with this direction, we will consider this as a x direction. This is the x direction. Is it okay? This direction will be considered as, this will be regarded as a x direction. Is it okay? This particular vertical direction we will use as a y direction. Is it okay? X, y. Vertical direction as a y, horizontal direction as a x. And if this any angle lamina is present with particular direction, then that can be studied here. Is it okay? So this is the failure envelope, and now with the help of this maximum strain failure theory, we are trying to identify this failure envelope. So maximum strain failure theory, so that is based on the maximum normal strain theory. So maximum strain failure theory is the basis, and that is given by Saint Venance. Is it okay? So that must be understand everybody, because that may be asked for a multiple choice question. So Saint Venance theory is the maximum normal strain theory. Whenever we use the word maximum strain theory, then that is the theory given by Saint Venance. Is it okay? So maximum shear stress theory by Tresca. So this particular theory, maximum strain failure theory, that is based on these both theories. Is it okay? Maximum normal strain theory given by Saint Venant, and maximum shear stress theory, that is given by Tresca, as applied to the isotropic material. Both the theories that are used in order to identify this failure strains by using maximum strain failure theory. Is it okay? So these three things we should understand first. First of all, maximum normal strain theory. Is it okay? So keep in mind maximum normal strain theory, and that is given by Saint Venance. Is it okay? And maximum shear stress theory. Is it okay? Maximum shear stress theory, that is given by Tresca. Is it okay? And both the theories which are applied to isotropic material, and maximum strain failure theory refers both these theories. Is it okay? Both these theories are referred by this maximum normal strain theory. Is it okay? That we should understand first. Then the strains applied to lamina are resolved to the strains in local axis. Failure is predicted in a lamina if any of the normal or shearing strains in the local axis of lamina equal to exceeds the corresponding ultimate strain. So that is the common, that whatever earlier we have used in case of machine design second, also you have studied this part, and there also the same set of equations were used. But here, whenever with these particular equations we are using for angle lamina concept, then the concepts of isotropic material theories inside this, the Tresca and the Saint Venance, so maximum normal strain theory and maximum shear stress theory, that are used as a basis for this maximum strain failure theory. Is it okay? And with that, this set of equations which are given here, it is minus epsilon 1c, epsilon 1t, epsilon 2c, epsilon 2t, all are ultimate. Is it okay? And epsilon 1 is the strain in direction 1, epsilon 2 is the strain in direction 2 here. Is it okay? So here you can use, here you can refer the values of this epsilon 1 and epsilon 2 here. Is it okay? So once again, if we apply the concept of this maximum stresses and maximum strain theories here, And if that values are plotted on the graph, then here we can understand this kind of graph is coming, and this graph is nothing but the failure envelope. This graph is nothing but failure envelope, and with reference to that failure envelope, we may consider that the material is stable, material is safe within this particular region. Whatever the region is shown here, in that region, this material is safe, but outside this region, material is not safe. So if the value of tau goes beyond this 24, it will not be regarded as safe. Likewise, for each and every case, means here, whenever the stresses and stresses in x direction and stresses in y direction that are taken for the references, minus indicates that these are the compressive stresses, plus indicates that these are the tensile stresses. In this case also, with this reference to 0, the minus represents the compressive stresses, plus represents the tensile stresses. Is it okay? So on both side of this 0, on both side of this 0 also, whatever the values of the stresses are given, so that values of the stresses, that will be the reference values in both compressive and tensile natures. Is it okay? So as far as concern with these values of normal stress strain theory, or this particular Tresca or the Saint Venant principle, these values which are referred here, and with this particular diagram has been drawn here. Is it okay? So whatever the concept of failure envelope which we have taken for the reference, same concept of theory of failure, the iron failure envelope, that is used here. Is it okay? So with usual notations, this strain 1 and C, 1 and T, 2 and T, 2 and C, that we know gamma 1, 2 is the ultimate in plane shear strength. Is it okay? So with this concept, today we will stop here, so that we can understand first of all maximum stress theory, maximum strain theory, failure envelopes. Is it okay? So anybody, any doubt in this particular part which we have studied up till now?
No, sir.